Hello everyone, welcome to another DaSSWeb. Today I have the pleasure to introduce Vitor Ribeiro. Vitor is assistant professor here at FEP. Vitor has obtained his PhD here at FEP, and his main interests are econometrics, industrial economics, and machine learning, in particular deep learning. I would like to thank Vitor for accepting to do this seminar for us, and with indeed a very catchy title, Truths and Myths in Multivariate Time Series and Panel Data. Okay, Vitor, the floor is yours, and once again, thank you for your availability.
Okay, Professor Maria Eduarda, it's a pleasure. I believe you are seeing my slides, correct?
Yes, perfect.
Sure. Okay.
Perfect. Well, yes.
Nice. Well, as you told, my name is Vitor. I am an assistant professor at the School of Economics and Management at the University of Porto, in particular, mostly in the econometrics group at the Department of Economics. From a scientific point of view, my research is divided in three different segments. I have one strand of research in which I only execute mathematics, regardless of being applied theory or abstract theory. A strand of research that is purely econometric, mostly for inference purposes. And I also have another strand of research in which I use machine learning models, and in particular deep learning models, essentially in order to satisfy two main goals, either prediction or classification tasks. This is the strand of research that I will be focusing today. And essentially, I will try to motivate this by claiming that, as you read in the abstract, essentially we have many machine learning models now coming into the spotlight. However, it's important to distinguish what is an imitation from what is an innovation, and within innovations, using and resorting to an industrial economics concept to make a distinction between what we call drastic innovations and non-drastic innovations, or radical innovations and incremental innovations. Bearing this in mind, I will show you what I believe to be two innovations that are considered drastic, okay, that were implemented by me jointly with one research colleague that is from the Faculty of Engineering, and from one former full professor from the Faculty of Engineering that unfortunately died last year. In July, Professor Pereira. Actually, I will use this seminar to say that he was the most influential researcher that I had in my professional life. And so in some sense, this is also a tribute to him. This seminar and all the ongoing research that I am executing jointly with Rui Gonçalves, which is my research colleague when I am analyzing machine learning and deep learning models. And to present you the importance of these two innovations, I will present a case study that essentially it will be published soon in an academic journal, and also a real life example that is related to Betfair, in particular the pre-live horse racing events at Betfair. I would like to say that I have started my research in machine learning, and in particular deep learning, not for academic purposes, but for private surplus gain. Okay, I never had the intention to become a scientific researcher on deep learning. My goal was simply to have additional money in my pocket, as simple as that. Okay, I bring here some factual data. Between 2017 and 2023, according to the Quantum Consortium, there have been thousands of machine learning models that were developed for multivariate time series, either for prediction or classification purposes, okay? The question is that from all these thousands of machine learning models developed, 99% corresponds to mere imitations or incremental innovations. So they are marginally increasing something that already exists. Only 1% of these models actually the creators have the willingness to apply to own an international patent, and 1 out of 10,000 actually are owners of an international patent and have a private gain in their private life, okay? At least during some period of time. My goal with this seminar is actually to show you something that I believe to be two innovations that are international patented and that ensure for a limited period of time some profit gains in my personal life as well as in Rui Gonçalves' life, my research colleague. The question is that there is a prerequisite that is important in order to make sure that the prediction or classification tasks in fact finds its ultimate end, which is to satisfy the classical hypothesis of homostaticity. So for instance, when I am in a setting of high frequency trading, if I do not satisfy this hypothesis, and what is this hypothesis? Essentially, any dependent variable in which I pretend to forecast or predict. I use any stochastic process is dependent on a deterministic component for regression model and the non-deterministic component, okay? So disturbance terms. And the question is that normally, some preliminary work normally done requires to check whether a given panel or cross-section is homostatic or not. In other words, if the variance associated to something that we cannot control that necessarily translates human behavior, if it's constant or not, you know? And in practice, we can only obtain any meaningful results, and we have the incentive to incur in any amount of effort if and only if that classical hypothesis is met. Otherwise, my claim is that we may develop efforts for inference purposes, so to obtain coefficients representing the influence of a given input on a given target, okay, but for prediction or classification tasks, in order to understand what will happen in the future, actually your effort is, in the absence of a better terminology, useless, okay? So I will show you my two innovations. The first one is we label it as hole padding, or in Portuguese, enchimento rolante. The most easiest way to understand what this innovation consists is essentially assuming that you have a multivariate time series problem, okay? And I have assumed here that I use a certain kernel of size 2 to analyze the data between 2000 to 2025, okay? So the idea is that, for instance, when the kernel reaches to the last year, 24, remember that the kernel has a size 2, so it will then cover the period 25, 26, okay? But the question is that the period 26 has empty cells. So the question is, how should we proceed, okay? And there are several padding methods to proceed under this circumstance, okay? We may simply empty the missing spaces with zeros, and we fall into zero padding. We can use valid padding. There are several padding methods. Our method, essentially, what it does is, it identifies the point in the time series in which the correlation of the last year achieves the highest degree. Okay, and so in some sense, this is an easy example to show the utility of hole padding. Okay, nevertheless, the utility of hole padding should be contextualized in a broader context, because in practice, hole padding is nothing more than an automatism that ultimately avoids to fall into what econometricians call the specification problem. So let's put it simple. Let's assume that I have a certain multivariate time series, okay, that exhibits cyclical properties. Imagine that I have some kind of cyclicality effects there. The common approach in econometrics would be essentially to introduce dummy variables, okay, that are representative of each specific week. Okay, so I introduce a dummy variable to represent a given week of the month, a second dummy variable to represent the second week of that month, and so on until I reach the the third week. And of course, if I introduce an independent term, I cannot include for dummies, okay? Because I would fall into the trap, into the dummies trap. Well, what happens is that the normally procedure that we took in the field of econometrics is we confront an unrestricted model with a restricted model, okay? And essentially, if the coefficients associated with the dummy variables that represent that cyclical pattern are jointly statistically significant, then in fact, that shows that something needs to be done. Either additive effects need to be included, or alternatively, this is why we resort to a deep learning approach, we can introduce role padding as an automatism that perfectly substitutes the utility of including in the deterministic component of the regression model additive effects. Okay, well, after this innovation, the second innovation, remember what is the abstract of this seminar about. This seminar claims that computer scientists usually adopt an opaque language that only computer scientists are able to understand. So I will try to do this exercise. In my second innovation, what I will do is I literally will read what this slide is telling you. And then I will explain this not in a computer science language, but from a statistical, econometrics, and mathematical point of view. And you will see that, in fact, probably what I claim, that computer science and its communication is most of the times too opaque, and therefore many researchers that have different backgrounds actually would improve this research field by having a better understanding about what computer science language tells us. You will, I will confront both slides and you will see the difference. So essentially my second innovation consists of the following. I transformed the multivariate time series that has a 2D or a bidimensional input map format, okay? So it's the time series for all the input variables. And I transformed this 2D map into a 3D input map, okay? That includes a segments component, okay? In doing this approach, essentially, I have the capacity to extract predicted values for a given target. Okay, that's the idea. Continuing, I say that I have the development of 2D maps of attention weights using convolutional layers, which are defined by time steps and segments components. And so this innovation, protected by international patent, essentially means using convolutional layers to build attention maps in order to make it possible using the size of the convolutional kernel parameter to define the extension of neighboring data of a certain point that contributes to compute the level of attention given to that particular point in this 2D map. Moreover, I also claim in this innovation that I split, okay, this process by having an attention map for each explanatory variable in order to increase the precision of the data. Well, given this slide, and essentially, actually, it summarizes very well what my innovation is about. I believe that 99% of people, even holding a PhD, don't understand absolutely nothing, or at least probably with a background in computer science, they may have some lights, but if they have a statistical background, an econometrics background, or a mathematical background, they will have difficulties in understanding which is the innovation about, okay? And therefore, I will now explain what essentially consists our innovation. Our innovation essentially consists of introducing within variation inside between variation in a given multivariate time series. What is this? Well, essentially, the concept of between variation and within variation is clear. Between variation means that for a given time period, I have the capacity to observe all the units of the sample. Within variation means that for each observation, I track them over time. Well, essentially, how can we introduce within variation inside the between variation? Basically, the time series are segmented in sequences. So imagine that I have weekly information about a given time series. If I also have information about each day within the week, then essentially I have the capacity to introduce within variation inside between variation. When I do this, when I essentially move from only having time series with a week dimension in order to have sequences of daily information for each week, then this is what it means to transform the 2D input map with variables versus time steps components into a 3D input map in which I observe each input variable over the time steps, but for each segment, the time steps represents weekly information and segments represent each day of the week. So our first innovation is this one. Moreover, so in practice, essentially all the subsequent benefits that we obtain by introducing within variation inside between variation actually become much more easy to understand, okay? Nevertheless, the main lesson behind this innovation is straightforward. The following benefits hold because introducing segments in a time series is basically equivalent to convert a time series into a panel date, okay? And this is one first innovation. So we don't see multivariate time series as a time series itself. We try to convert this into a panel data problem by introducing what we call and what computer scientists call segments, or in other words, converting 2D maps into 3D maps, okay? Moreover, the innovation consists also of having a map associated to each explanatory variable. So the standard approach in computer science is to work on top of dense layers, or in econometrics language, the standard pooled OLS regression, where essentially we put everything in the same basket, okay? By doing an individualized attention map for each explanatory variable, this allows me to retrieve information about the impact that each input, that each explanatory variable has on the target, which is important because essentially we may have the incentive, depending on the problem we have in hand, to introduce, for instance, fixed effects or random effects, which is something that is antagonic to the presence of a standard pooled OLS estimator, okay? So essentially in econometrics, we see pooled OLS as one extreme in which one independent variable in the deterministic component of the regression model stands for all the individuals of the sample. In the opposite prism, we have essentially the imposition of fixed effects when all the units or observations of the sample exhibit what we call unobserved heterogeneity, and that is how we control for that unobserved heterogeneity. In between both extreme cases, we may have incentives to introduce random effects, so which is the case in which the deterministic within the deterministic component of the regression model, the intercept is not correlated with the set of regressors or input variables that are used to predict and forecast the behavior of our dependent variable or target. Okay, well, the question is that I know this is difficult to explain in short minute of time, but this was my approach. It will become more easy once you see the real world cases. But this innovation, so the possibility to introduce convolutional layers inside an attention block, individualized per explanatory variables, brings an important opportunity for computer science works, which is to introduce fixed effects, random effects, not only in single dimensionality levels, but in multiple high dimensionality levels, depending on the case study we have in hand. For instance, in the case study that I will show you, the last case study, I may have incentives to introduce, it's the pre-live horse racing at Betfair, so I do have incentives to introduce fixed effects at the horse level. But for instance, at the race level, I have different horses that belong to a given race, and since they are exchanging over races, I do have the incentive at a higher level, so at the level of the race, to introduce random effects. And therefore, this is something that we believe is a technical requisite that the econometrics literature is currently missing, and the flexible framework built on top of a deep learning architecture allows to create. Moreover, there is also an important advantage of within each explanatory variable to introduce attention mechanisms, okay? And the idea is the following, okay? Normally, in a standard discrete choice analysis, okay, what happens is that individuals or units of our sample consider all the available options, okay? What happens is that when we have attention mechanisms, okay, and the standard attention mechanism in particular, what it does is it looks at the entire choice set and it gives us information about which inputs are more important to explain the context. So in addition of obtaining coefficients that represent the effect of a given input on the dependent variable, we also have information about the relative importance that each input has in a given context, okay? Well, this is something that has been actually published recently in a top journal from the field of economics, in the Quarterly Journal of Economics, by these two authors, okay, that belong to the Yale University. The question is that, and this is what I will claim, the innovations that I have developed jointly with Rui Gonçalves and Lourdes Pereira actually improve the state of the art in the econometrics field, okay? And you will see in a minute. So this is probably, even for you, even for me, that I am explaining this for the first time, I don't know if it was the best approach, but essentially I have described you the two main innovations that I bring, not only to the field of econometrics, but also the field of computer science. But most importantly, now you will realize the benefits in two real-world cases. The first one purely academic, and the second one, essentially, it's the case study that motivates us to develop this kind of architecture. In terms of the case study, I will essentially show you the application of our two innovations into the this UCE data set, which is concerned with forecasting the electric power consumption of a house located in France. These authors, so this is publicly available, and normally computer science studies actually execute this approach. Normally we use some known data set and we test our innovations in order to see whether we improve the metric or not, an error metric or any other. Okay, so in this particular case, for academic proposals, we use this data set, where essentially the output is the global active power. Okay, it's essentially an output that tells me how much electric power is consumed by that particular household. And then I have this set of inputs: global reactive power, voltage, 3 submetterings, and global intensity. What we have done initially is essentially some feature engineering work. We convert minutes to hours, okay? And we construct examples that essentially consists of historical information about 1 week in order to predict what happens in the first 24 hours of the first day of the following week. So essentially what this means is that I have a total set of inputs that corresponds to 168 hours, and our goal is to predict what happens in terms of household consumption, power consumption, for the average of the next 24 hours. We do here standard feature engineering work. We split the sample for training, test, validation. The validation corresponds of 286 days, okay? But most important, so by the way, in terms of input treatments, I put here this figure just to shed light that noticed how the raw data was. So without any pre-processing, it would be impossible to forecast something. With with the standardization technique, so in which we retrieve the means and divide by the standard deviation, you will see that, for instance, in voltage, I still have problems. With the approach that we took at the input level, input treatment level, which is to apply an histogram truncation at the 5% with rescaling of the input set. For instance, here at the output level, we use the activation function, which is the tan with values normalized between -1 and 1. So we have done some feature engineering work in order to make sure that we have good data to work with, okay? But nevertheless, this does not remove quality for the two innovations that I have introduced and that I will explain in detail in a minute. Nevertheless, before moving into the main benefits that our innovations bring, we need to understand how deep learning approaches work, okay? We may have different layers that we can use in a deep learning architecture. The most standard one is the so-called dense layers, where essentially this is like in econometrics, the standard evolution of a stochastic process in which I have a deterministic component and a non-deterministic component. Okay, here computer scientists call to this beta bias. So essentially I have some output that I will predict that is based in a set of inputs, and I also add a bias which is representative of what we call the human behavior, something that we are unable to control. On top of this standard layer, we have also convolutional layers. The difference in convolutional layers is essentially that we have a kernel of a given size that runs the input set in order to obtain output predictions. Better than only seeing the mathematics, probably an animated GIF is more interesting to realize how convolutional layers work. So if, for instance, here I have all the inputs, imagine input 1, input 2, input 3, input 4, input 5, and then here is the time dimension, essentially with a kernel, in this case, a 3x3 kernel, I run the set of inputs and I obtain a given outcome. And this is essentially how convolutional layers work, okay? On top of convolutional layers, we can also have what we call recurrent layers, or in particular, long short-term memory, LSTM layers, where essentially this is like an evolution of the standard time series models like the REMAX and similar. The idea is that from a mathematical point of view, I predict what will happen in the subsequent period based on a set of inputs and a weight that not only covers this set of inputs, but also based on some information that is stored in a memory cell. So the idea of a recurrent layer is that I can and I am able to introduce what we call in econometrics language dynamic effects. So based on past information, I can obtain innovative information about future outcomes while preserving in memory cells the relevant information, okay, to have better predictions or better classifications, okay. Moreover, I can also have both. So the standard layer, in addition to the standard dense layer, in addition to convolutional layers and recurrent layers, I can also combine both. This was done in 2015 by a group of Chinese researchers in which their goal was to predict the rainbow intensity, okay? This is called the conv-LSTM2D layer, where essentially I combine convolutions with the LSTM framework, okay? That's the notion. The difference is that, so imagine here different inputs, and here the conv-LSTM2D layer. The difference is that with our innovation, we are able to split the time dimension, based on sequences. So imagine that this particular square represents all the inputs over 1 week. What happens is that essentially we introduce segments per day. So that's one important feature that we do, because our goal with our innovation is to improve the attention mechanisms by, and you will see in a minute what we do. So essentially, each sequence here, this represents, for instance, the Monday, the Tuesday, the Wednesday, Thursday, Friday, Saturday, Sunday, rather than having all the time step combined together. Well, given this, what the missing part in the deep learning framework is to explain you the attention mechanisms. So I started this seminar in a rush by explaining you what were our innovations. But the question is that so far you do not understand well which is the special improvement or innovation that we bring. And now it will become clear to you. Okay, so the standard attention mechanism that is associated with transformers, so the standard attention mechanism that comes from a paper of 2017 that is entitled "Attention is All You Need." Essentially what it does is, in addition of having in the end, as I have told you, that's the premise, the capacity to obtain the coefficient or parameter that represents the influence of a given input on a given output, I can also, within the set of inputs, attribute what we call context weights. So in a given context, I may have more influential power of, let's say, input 1 relatively to input 2 relative to input 3. Okay, the standard attention mechanism is precisely this. So in the context of a dense layer, okay, it will give me attention weights. It will tell me, okay, input 1 has a relative importance of X, input 2 has a relative importance of Y, and so on, depending on the set of inputs, okay? So it does not discriminate for each input a specific attention, okay? What we do in our innovation that is intellectually protected by a patent, by international patent, is to introduce this specificity. That is, once we segment the time steps by sequences, we can focus on each input variable. And I can introduce, essentially, after personalizing an attention map for each individualized input variable, I can introduce two types of convolutions, okay? I can introduce what we call a one-dimensional convolutional attention layer, or I can introduce conv2ds, so v-dimensional convolutional layers. In which consists the innovation of introducing convolutional layers inside an attention block? Essentially, rather than looking at all the inputs and understanding the relative importance of each input, what this does is I am strictly focused on, let's say, input 1, and I will see if the time dimension, if the time steps dimension is in weeks, I have the evolution of input 1 in week 1, week 2, week 3, week 4, and so on and so on. And essentially, this convolution will attribute a weight of attention for each week. Okay, so input 1 in week 1 has an importance of, let's say, 10%, in week 2 of 20%, and so on and so on. Okay, so essentially, rather than introducing an attention mechanism through a dense layer, we introduce an attention mechanism by means of a one-dimensional convolutional layer in which the input is observed over the time step dimension, in this case, over weeks, okay? Differently, a convolution attention 2D acts differently. Essentially, since we have introduced the possibility to, so within each week, if I assume that the sequences or the segments are days, okay, so within a week, I have Monday, Tuesday, Wednesday, and so on. Essentially, a conv2d gives me the relative information, okay, for each day of the week. So for input 1 at week 1, Monday has an importance of X, Tuesday has an importance of Y, and so on, until all the segments of that particular time step are fulfilled, okay? And essentially with this, I think that it becomes clear to the audience, even not entering into specific details on how to program, the precision of the analysis, the minutiae, it is much more higher, because within a multivariate time series, we convert it into essentially panel data by having multiple segments, and within each segment we attribute the relative weight of attention, and this is individualized. This is not considering all the set of inputs in the same basket, but this is done for each individual set input, and therefore of course, as you will see in the main results associated with this case study, the precision of the data allows us to obtain, in this case, lower error metrics, since we are in a prediction framework, okay? By the way, this is important. We have and own the international patent of these two types of convolutional layers inside the attention block, both the conv1D and the conv2D attention. And essentially, bottom line, and not entering into specific computer science details, the idea is straightforward. Just to make things clear, we have a given multivariate time series, so multiple inputs to explain a given output, okay? The first thing that we do is we may have the incentive to introduce segments, so to convert the multivariate time series into a panel data. And then, after splitting my input set by explanatory variable, okay, essentially I may have the incentive to introduce attention mechanisms associated to each input. And these attention mechanisms are executing by means of convolutional layers, which may be 1D if I track one input over time, or maybe 2D if I track a given input, not only over time, but within the time step for each one of the segments that define that particular time step. Bottom line, this is the innovations that we have created. On top of this, we also have hole padding, because in this particular case study, hole padding sometimes works well, other times it's irrelevant. But in this case, it works well. Why? Because we observed that the pattern of consumption, of electric power consumption, was cyclical. In particular, every week, the household had the similar pattern of consumption. And therefore, rather than simply introducing dummy variables in the deterministic component of our regression model, we can apply the hole padding that automatically brings or becomes, is a perfect substitute of the introduction of dummy variables, because it correlates, let's say, for instance, the Sunday with the Monday. And therefore, it allows to, if you want to see this in a more easy way, while the dummy variables approach consists of introducing cyclicality in static terms, hole padding does it in a dynamic context, which we believe is much more powerful when the goal is to predict or classify. Well, so bottom line, this is the example of our innovative architecture. In this case, so once I have here a conv-LSTM 2D, we do the segmentation by input variable. In this case, in this example, this is only for illustrative purposes. We have 5 inputs, okay? Input 1, input 2, input 3, 4, and 5. And for each input, I have an attention map, okay? And I apply conv2D or bidimensional convolutional layers in order to have the capacity to extrapolate not only the influence of that particular input on the target, but also the relative attention that each sequence or segment has for each time step, okay? In this case, the importance of each day for a given week for that particular input. And this applies to all the set of inputs. In the end, what we do is a concatenation such that then I move my architecture, and in the end, we finalize with a dense layer, essentially because our goal is simply to predict. We can also transform this into a classification problem, for instance, by introducing a softmax. Okay, well, in terms of results, and please take into account that even for myself, that I am one of the creators of this architecture, it's really difficult to explain this in an easy way, to be understandable by people that are not necessarily from the field of computer science. That is the concern of this seminar. My goal in the end of this seminar, and I hope to succeed, is to make sure that people that are not necessarily from the field of computer science feel themselves confident on trying to develop something in this field, okay? Because it is honestly my conviction that even more important than coding skills, and clearly you need art skills in this particular field of research, you really need to have a strong statistical, mathematical, and econometric background to know why do you introduce innovation A or innovation B. Otherwise, you are a mere programmer, okay? And in this case study in particular, so in predicting the electric consumption of that particular household, whose house is located in the south of France, I guess. Clearly our innovation, so the application of a bidimensional convolutional LSTM model with the bidimensional convolutional layer attention mechanism inside the attention block, essentially gives us the lowest error metrics compared to other cases that we have inspected. We have inspected the standard Arimax model, the WaveNet, TCM, LSTM, several variants, and essentially our two innovations, the whole padding and the introduction of convolutional layers inside an attention block, allows us to reduce the error and so to have honestly good predictive forecastings. Nevertheless, an important point here is to realize that these results are also improvements compared to past studies that have analyzed the same data set. Okay, in this case, I have here the validation data set, just a graphical illustration to confront the real and the predicted. Nevertheless, I should say, although it is a common approach in computer science to compare different studies, metric results, of course, I think that it may not be optimal to do it so. And the reason is actually straightforward. There are so many things that can be manipulated by the authors that ultimately I think that a study should be worth by its innovative character rather than just by the fact that the metric has decreased. Okay, in this case, we have achieved state-of-the-art results, but actually for us, it's irrelevant. For us, for the creators of this study, the main point is to make sure that people understand the beauty behind transforming a multivariate time series into panel data, the beauty of doing a split of the set of inputs by explanatory variable. Within each explanatory variable, that different types of convolutional layers and attention mechanisms can be implemented, and to make sure that these specificities are actually the precious thing behind the development of deep learning, of this deep learning architecture, due to the greater precision in the analysis and in the treatment of inputs and output forecasts. Given this, I would honestly like to show you, because as I told you in the beginning of this presentation, more than doing academic work, I was not motivated to bring myself into the field of deep learning by academia, okay? I was motivated by a real world case and by profitable proposals, okay? And you will see in a minute why this is so important. I will talk you about something that, during my PhD, I applied, like a divide and conquer strategy, in the sense that my specialization is purely mathematical. And I always was, I believe, a very good student. I always had very good classifications in mathematics. But the question is that at the time, and now I am even more aware, I was incapable of creating something new. I was a mere imitator. And therefore, I tried to incur in the cost of understanding mathematics. And in some sense, I had lucky with my advisors because I really became a better mathematician, I guess. But meanwhile, in my private life, I always try to apply what I believe to be the things in which I had more skills. So econometric work, and I start seeing some embryonic evolutions in the field of machine learning, okay? And essentially Betfair was a market that I was constantly watching while I was a PhD student. So on top of my mathematical research, I also liked to see many horse races, and particularly the 10 minutes window before a race begins. Why? Because under that specific circumstance, the market is purely speculative. Not here in Portugal, but for instance in the United Kingdom, there is and in general in Commonwealth countries, there is a lot of passion regarding the horse races and similar ones. And so in some sense, given that they are betting before the race begins, that's a pure speculative market. And in a pure speculative market, in a closed system as that, we may have a profit opportunity there. And so our goal, by applying these two innovations, deep learning architectures, was to predict the evolution of the algorithm. And in fact, the only thing that we use is, so we collect data each 5 seconds. We were collecting data from Betfair, okay? So we had a data set of 3 gigabytes, millions of observations. This is important to acknowledge. And we essentially had as dependent variable the price. So essentially, we don't call it price, we call it ticks in the Betfair market in particular. And our independent variable was liquidity. From an econometrics perspective, what we need to do in order to have any predictive ability is first to introduce dummy variables. Why? Because to introduce dummy variables, we can distinguish the different ticks that compose a given ladder in which demand and supply, so bets against or bets in favor, are in equilibrium, okay? And normally, how can we do this? Well, the way we have done this actually is quite interesting because if you are aware, imagine that this is the reason why I have here this triangle. Imagine that I have here, this is period T and this is period T plus 1. And so the price moved from this point to this point. Essentially, in order to capture whether I change from a tick representative of the price 1 to the price 1.02, for instance, I can use or take advantage from an angular coefficient, where essentially the amount of the price changed corresponds to the tangent of that angle. And essentially what we have done, from a theoretical point of view, we have done something more powerful. But from a dummy variables approach, if the angle is between 0 and 5 degrees, okay, I am still in the same tick. Once the angle is between 5 degrees and 10 degrees, then I can introduce a dummy variable there that takes value 1 if the angle is between 5 degrees and 10 degrees, 0 otherwise. Then, if the angle is between, for instance, 10 degrees and 15 degrees, then I move to the tick upwards. And this is how I can essentially introduce additive effects to cover all the ladder, okay? The question is that the evolution of the angle is not constant, okay? Because essentially the degrees of the amplitude tend to decrease as I move upwards in the ladder, okay? And so the beauty behind roll padding, so by the way, just 1 minute, before, on top of adding additive effects that essentially are time variables that capture each one of the ticks that compose the ladder, then our goal is to cross each one of the ticks, each one of the dummy variables with the amounts of liquidity. Why? In order to have multiplicative effects, in order to have a notion of the liquidity per tick in the entire ladder. Notice that our goal, why do we want to have a notion about the liquidity at each tick of the ladder? Because naturally our order is different depending on whether a given tick has more liquidity or not. Essentially in ticks where the liquidity is greater, I may have the incentive to have a higher bet, okay, to be engaged or to put a higher bet against or in favor of that particular evolution of the price. It may go up or down. On top of this, okay, the main advantage of hole padding now is clear. It's impossible, I believe, to have any predictive capacity by following a dummy variables approach, okay? The dummy variables approach and the introduction of additive effects and multiplicative effects is extremely useful for pedagogical purposes and is extremely useful for academic work, in particular for inference. But when we have, in the absence of a better terminology, money up on the table, we need to have an automatism, and even better, we cannot be working with a static concept as the dummy variables approach is. We need to have an automatism that automatically gives me information about the dummy variables representative of the entire ladder, because essentially, by definition, under high frequency trading, the price is dynamic. The tick in which demand and supply are in equilibrium, that is constantly changing. And this is the main advantage of hole padding. Hole padding essentially introduces dynamism in a static variable dummies setting or framework. That's the main advantage of hole padding. On top of this, notice that in this particular case study, we wanna, so notice that in the deterministic component, I have liquidity per tick, and the additive effects. We also have the need to introduce fixed effects and random effects. Fixed effects, why? Because at the horse level, horses exhibit different characteristics, okay? I am not at the race, okay, yet. I am in the 10 window before the race begins. But the question is that you have many bettors there that are sentimentalists, and so they may exhibit a certain preference by a given horse. So it makes sense to impose fixed effects at the horse level. However, since by definition, the number of horses and the type of horses that are in a given race changes across races, then it makes sense to impose random effects at this higher order level, at the race level. And so it becomes clear why our innovation was so important. We have a segmentation of the set of explanatory variables, okay? And within each variable, we have the opportunity to have attention mechanisms that track the evolution of the horses over time, in the case of a convoluted attention mechanism, or for different types of segments. In this case, segments are different moments of the day in which a given horse runs, or different days of a week in which a horse runs. We can apply convolutional to the attention mechanisms to observe the relative importance that each input attributes or gives to the context, okay? And on top of this, we also have the possibility, since we have split the input set by explanatory variables, to introduce just one attention map focused on the introduction of fixed effects and random effects. And so, of course, even for myself, that, and this is true, we spent 1.5 years of our life implementing these. So trying to explain this to an audience in 30 minutes is honestly challenging. But I mean, I think that if I did not succeed, please alert me, because I will try to explain more meticulously. Nevertheless, what was our goal? Our goal was to predict the evolution of the odd 5 seconds ahead. So in high frequency, essentially, we collect the data from Betfair. Each 5 seconds, we add information about the prices and about the amounts of liquidity. We also have more information actually about volatility and so on. We constructed a richer data set. But the question is that we essentially combined all the information in a 50 seconds window, sorry. And only then we have done a segmentation by segments of 5 seconds. And essentially, why do we claim and how can we have any chance to predict with accuracy the final result? Well, the idea is clear. I can only predict, if I predict the evolution of the odd 5 seconds ahead, then this means that I have an information advantage. So I am the first on the queue implementing an order, and therefore that's the only chance I could have a profitable opportunity. However, even most importantly than that is to ensure that the most basic assumption is met. And the most basic assumption is, given that you have a data set of millions of observations, your data set must satisfy the classical hypothesis of homoscedasticity. Why? Well, the reason is straightforward. When I have a certain output that follows a certain stochastic process, I have a deterministic component and a non-deterministic component to explain that particular target. The deterministic component, okay, we have implemented very good innovations. They are actually protected by international law, nice. But the question is, the non-deterministic component, so the disturbance terms that necessarily reflect human behavior. So in practice, I may have some random better that starts doing random bets or bets that make the variance associated with a non-deterministic component, the volatility not being a constant. Essentially what this makes is in case of not predicting well, you may lose a considerable amount of money. So the idea is straightforward. Imagine that in period T I buy, okay? If the price increases in period T plus 1, okay, you make a profit. But the question is that for some reason, the bot that you implement may also fail, and therefore the price may decrease and you may have a loss. But the question is that if the classical assumption of homoscedasticity is satisfied, then at least you know that your losses are bounded. And essentially, the secret of succeeding in high frequency trading is then straightforward. The only way you can make a profit is actually to ensure that your losses are bounded. Well, the question is, I don't know actually why I never have listened this in any of the available YouTube videos, for instance. Many people that work in prediction of the odds, well, I don't know why they don't do this. Probably they are unaware of the presence or of the necessity to have an homoscedastic panel in order to truly be able to make a profit. Because look, it's also important to say another thing, and as an academic and as a professor, particular to the undergraduate students, I have that concern, which is, notice that when we are teaching econometrics and when we are analyzing a chapter related to heteroscedasticity, normally we say, okay, look, we have an heteroscedastic sample, we can restore the classical hypothesis of homoscedasticity by doing this transformation, so on, and therefore we can obtain still unbiased estimators, so the blue estimators remain valid and so on. Okay, that's true, but that's true for inference purposes. The question is that if your original data set is heteroscedastic, then regardless whether you recover the classical hypothesis of homoscedasticity, the original data set will remain heteroscedastic. So in practice, your original data set, if for some reason you buy and you have the conviction that the price will increase, if for some reason the price decreases, you may incur in a loss, and you may incur in a huge loss, such that ultimately your model may not have predictive capacity. And this is simply because the basic premise, the satisfaction of the classical hypothesis of homostaticity, is not met. Well, what happens is that in this real world case, me and Rui, we had the opportunity to have positive profits for a short period of time. Okay, the question is that after 1 month operating, we incurred in permanent losses. And so my decision was straightforward. I left the markets. I abandoned high frequency trading. In fact, we tried to update the data set, okay? But the question is that, contrary to the first data set, the classical hypothesis of homostaticity was no longer met. So essentially, I applied several tests, not only White's, but also Bruce-Pagan's tests, also some recent heterostaticity tests developed by Chinese researchers. Well, that classical assumption was not satisfied. So it was clear to us, we were in 2018, that essentially we had a good profit opportunity here, but high frequency trading was not sustainable because of failing to satisfy this classical assumption. Well, at that time, we had a meeting with Lo Pereira, I still remember, and our goal was to see, okay, next steps, what are we going to do, okay? Once I actually told Rui, probably I will become a YouTube guru, because at least I can show my profit gains at Betfair, and we can become sellers. That was our in our private conversations, we used to say this. But then after having, you know, a serious meeting also with Lo Pereira, with his knowledge, we actually decide, since we know the strengths and the weaknesses associated with our deep learning architecture, what we have done is we spent 1.5 years developing this framework, this architecture. Then we spent another 1.5 years in order to own the international patent for both innovations. We were also strategic in the sense that at the time we developed a paper that ended up being published in the Information Economics and Policy, in which essentially we say that applying standard deep learning architectures would not make it possible to have predictive capacity. And in fact not, because if the classical hypothesis of homostaticity is not met, it is our conviction that it is very unlikely to truly predict the future. And so what we have done essentially is to, since we were aware at the time that particularly generative adversarial models, and the most recent example is ChatGPT, would have and was going to have a heap in the upcoming future, we decided to protect ourselves essentially by owning the international patent of both protections. And only now we are trying to developing papers, seeing in which kind of fields this fits better, okay? Just to finalize, I don't know if I have missed my time, sorry, but just to finalize, main conclusions. AI is good to increase the productivity in repetitive tasks. The main example is role padding. AI is not good yet to develop complex tests. Actually, there is one Nobel Prize in economics that explains this very well. We have two different types of systems in our brain. System one is logic and slow. System two is fast and rational. AI currently only has the ability to manipulate system two. The logical only comes from the human brain. And in fact, what AI is doing currently is to sharpen the inequality between high quality research and low quality research. That is my conviction, because since high quality researchers have the capacity to be guided by AI models and AI intelligence, essentially they may have a strategic advantage there. And so, in some sense, my conclusion is that AI should be explained in alternative languages, more easy to bring more researchers to these fields, to disseminate radical innovations rather than imitations. And therefore, I would say that AI ideas require the linear model. First, private gains. If I have private gains, protect yourselves. Only then go to financing. Otherwise, here you have a problem which is burning money from the public heritage, rather than the standard approach, which is I have an idea, I ask for money, I protect my intellectual property rights, and only then I see if I get private gains. Well, I think that this is, I mean, I am nobody, but I have an opinion based on my efforts. And so I think that something needs to change here. And well, given this, I can only thank you. Feel sorry for my lousy English, but, and of course, my goal is to trying to be as much as precise as possible, and at the same time, not to be excessively unattainable in the sense of being understood by others. So I am here willing to answer to your questions now. Thank you.
Thank you, Victor, for your interesting talk and presenting us all your new developments. And the floor is now open for questions or comments, please.
First of all, sorry for having passed the time. I was not even aware, but of course. Well, don't worry.